Over the next couple of assignments, you're going to be working on exponential growth and exponential decay. And before we get into it, let's relate it to something you're already familiar with. You're familiar with y equals mx plus b. B is your y-intercept, m is your slope, and you end up getting a straight line out of this. Well, what we're going to switch to is exponential growth and decay, and it's going to follow a general formula like this. And when you look at a formula like this, you'll have numbers where the a and the b are, but the a is going to be your starting value, and the b is going to be the rate at which you grow or decay. So if we're in exponential growth, the a, your starting value, would be your spot on the y-intercept, and then we're going to grow exponentially, which means you're not going to have a straight line like you did in the y equals mx plus b days. You're going to have a curvy growth path, or if it's an exponential decay, which means your values are getting smaller, you still start out at a spot on the y-axis, but the b is going to give you a rate at which the values decay or decline. Neither of these, exponential growth or decay, will be linear. They will always be curvy. So when you look at these situations, one of the things you'll look at is the value of this b. If it's larger than 1, you've got yourself exponential growth. If it's smaller than 1, you've got yourself exponential decay. So with this example in the green, I have a situation about 20 bacteria in a colony, and they're doubling every hour. It's going to take a little practice to get used to turning these words into equations, but basically 20 is the starting value, the a, and the growth rate is this. They're doubling every hour, so that means you're multiplying by 2 times 2 every hour. So you could write the equation this way. If you like just y's and x's, you can write it that way, or good old function notation, the number of bacteria at any given hour, and then you use h as your variable. I'm going to give you an example of exponential decay over here. 6,000 players in a tournament, maybe an online video game tournament, and half are eliminated after each round. So when you read that situation, you say, okay, we must be in a declining or a decay situation. 6,000 is my a, my starting amount, and my rate at which I'm having growth or decay is half are eliminated, so I'm multiplying by 1/2 each round. I can write it this way, or this way. They're all saying the same thing. But my eyeballs look at this to tell me growth or decay, bigger than 1 growth, smaller than 1 decay. And my eyeballs look at this or this to know the starting amount. So we'll go through some more examples, and I think you'll start to see how you can change words into equations and then graph them and so on. I have $400, and it's invested into an account that will increase in value by 8% per year. So I know that since my investment value is going up, this is exponential growth, and I know my starting amount is 400. So the value of my account is, you can think of this as your A, and now we need a growth rate, B. Well, my starting amount, A, that's pretty easy, but my growth rate is a little tougher. If I'm growing at 8% a year, remember this growth rate number has to be larger than 1. So it's basically the 1 that I had plus 0.08, because 8% as a decimal is 0.08. So turning that into an equation, kind of rough, because converting this 8% into 1.08 can get people. But if you looked at this and were asked, is this growth or decay, you would definitely say it's growth, because my growth factor is larger than 1. Let's look at this. Actually, let's take a look at this if I were to graph it. As I mentioned earlier, these would not be linear graphs. They would be curvy. And so 400 is my starting value. and it's experiencing growth. So the value of my account would start up slightly, but then it would increase quite rapidly eventually. And if you wanted to know the exact path, then you would go ahead and fill out a table. You'd plug in a 0 to your equation, get out a 400. You'd plug in any value. So for example, if I plugged in a 4 into my equation, I should get out a value of 544, which I can think of as the ordered pair 4, 544, which would mean at x equals 4, I go up 544 units. It's quite a trip. Oops. At x equals 4, the y value is 544. And remember, I get that information by literally plugging in a 4 and then doing the math to see what that gives me. In this case, I would probably do a 1.08 exponent 4th power, and then I would multiply that by 400, and there's that 544 I was talking about. If you carry that out for a bunch of values and get a bunch of points, you would verify this curvy growth path. Here's another example. A puddle is losing 20% of its volume each hour. The sun is causing it to evaporate, and it started with 2,000 cubic centimeters of volume. Right, so I look at this and I say, okay, I must have decay, exponential decay, because this puddle is getting smaller or decreasing. So now I think about my A and my B raised to an exponent. The A is your starting value. That's how much water was in the puddle. Now the 0.8, that might be a little rough, so let's take a look at this. Remember that this value, your B, has to be greater than or less than 1, and if it's decay, it has to be less than 1. 20% as a decimal is 0.20, so I have my 1 minus 0.20. That's how I get that. Words to equation might be kind of rough, but if you looked at this equation, you should be able to identify the starting value and the fact that we are decreasing. If I went ahead and started plugging in different hourly values into that equation, I'd get out different volume values, and my graph would end up looking something like this, exponential decay. Now you might see these equations without a starting value. So if you look at this 4 is really your B, because if I think of A, B to the X, my A in this case is a secret 1. You can't even see it, but it's there. The same thing over here. This 2/3 is my B, so I can think of this as y equals 1 times 2/3 to the x. My point is, if you see something attached to an exponent, that's your growth factor. That's your growth factor. And if there's not a coefficient in front of it, then it's just a 1. My growth factor is bigger than 1. I have exponential growth, and you could figure that out by making a table. My growth factor of 2/3 is less than 1. So if I go ahead and crunch the numbers, I see that my value is going 1, smaller, 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 and it would be following that type of path. One final example brought to you by your science class, or how the world works. A radioactive substance is having a half-life of 5 years, and it begins with a mass of 4,000 grams. As your science teachers love to tell you, a half-life means the volume or the mass of the blob reduces by half, in this case every 5 years. If something had a half-life of 20 years, then every 20 years the amount of substance would be reduced in half. So I want to find out the mass of this big blob after 20 years. Well, if a half-life is 5 years, that means I must go through 4 cycles of my half-life in those 20 years. 5 years, then to year 10, then to year 15, then to year 20 makes 4 cycles. I can represent that situation with an equation, and it's following the AB to the x idea. A times B to the x. A is my starting amount. My half-life, anytime something has a half-life, it always goes to half of its previous amount. So my factor is 1/2 raised to the x. Now be careful here because the x is the number of cycles of your half-life. So I can't really plug in a 20 for 20 years. I've gone through 4 cycles of my half-life, so I'm going to plug in a 4 and get 250 grams. This is how I would solve this problem via equation. This one's easy enough that you could just literally write it out. If I started with 4,000, oops, I screwed up. I'm going to have to change those. Okay, I fixed my boo-boo. I was talking about that you could do this by equation, or you could, because the numbers are friendly, just reason it out. 1 half-life would send 4,000 grams down to 2,000 grams. I've completed 1 cycle. I complete my 2nd cycle, my 3rd cycle, my 4th cycle. I keep dividing in half. You'll notice this is basically a geometric sequence because I have a common ratio of multiply by 1/2. In fact, all these exponentials are some form of geometric. But the point is, you could reason this one out by yourself. Your science teachers may also have a separate formula that looks like this, where x would represent the number of years, in this case 20 years, divided by 5 years per half-life, divided by 5, and this would still end up giving you 250. If you're used to that and understand it and like it, that's totally fine. If you prefer this method, that's totally fine as well.